Okay. So this is the tutorial. And we have 4 questions here. I think there is a 3 dots on my icon. If you click that one, you can see the pin option. Okay, then I think you can see that my camera has a full screen. Anyway, I think if I record this, it will be okay. I have checked it later. Previously, I have checked it. Then I will upload the recorded session also. I think it will be okay then. Okay. And okay. Now I have shared the paper. Okay. Okay. Now this is the tut we have. Okay. I have uploaded this to the LMS. If you visit it, you can download the paper. Okay. So there are 4 questions. Okay. Actually, the fourth question is related with the Z transform. I think we have done many this kind of questions. Okay. So mainly I will focus on this first 3. If I have times, I will also will do the 4th question. Okay. I hope you can do this by yourself without issue. Okay. The Z transform question. Okay. Okay. So we will start. Okay. So our first question is related with the sampling. Okay. So the question is, we are given a digital communication link. Okay. And it is said that that link capacity, the data rate of the link is 10,000 bit per second. Okay. Is that okay? Because several transmission, so this transmission line can be a guided or unguided media, we don't know. Okay, that information is not given. Okay, but the data rate is given, that is 10,000 bit per second. Okay, so you know that several transmission line have several capacity data rates. Okay, for example, if you get the coaxial cable, you will have around 100 Mbps data rate. Okay, but if you have an optical cable, you will have around 1 terahertz, 1 terabit per second data rate. Okay, so different transmission media will have different data rate and capacity depend on its their properties. Okay, so anyway, this transmission line given the given transmission line has 10,000 bit per second. Okay, and each input sample is quantized into. Okay, so we will move to the question. Okay, so I will stop the share. I will stop the share and get back to my camera. Okay. Can you see? Okay. So if I write here, I think you can see, no? Can anyone feedback, please?
Yes.
Okay, thank you. So we are given a transmission line. Okay, it may be a guided media or non-guided media. We don't know this kind of transmission link, maybe. Okay, and it is said that the maximum data rate is 10,000 bit per second. Okay, I will write with letters. Okay, 10,000 bit per second. Okay. Okay, and it is said that It is said that it, okay, each input sample is quantized into 10, 100, 1024 different voltage level. Okay, so you can see that this is a digital communication link. Okay, this is a digital communication link. Okay, this is a digital communication link. Okay, so it will carry only bits. Okay, it will carry only bits 1 0 1 0, so on. Okay, so if you have a analog signal, okay, if you have analog signal, we don't know. Okay, so this analog signal will be our baseband signal, information signal. Okay, it can be a voice, it can be an image, or it can be a video or something. Okay, it can be a text or something. Okay, we don't know. Okay, so anyway, if you have an analog signal like this, okay, you can't send that signal through this line. Okay, because this is a digital line. Okay, and we have to convert this analog signal into a digital signal. Okay, for that we have to use, you know that we have to use the analog to digital converter. Okay, ADC we have to use. Okay, so we have to use the ADC. Okay, so if you send this signal, I think we have learned about the ADCs. Okay, the step in analog to digital converter. Okay, first it get the samples. Okay, with some time. Okay, with some specific time. Okay, this time is called sampling time. Okay, this time is called sampling time, and we have this sample. So these are samples. Okay, these are samples we have. Okay, so the next step is this sample should be converted to a binary value. Okay, converted to a binary value. Okay, now it is said that each sample is quantized into 1024 level. Okay, so these samples, this any samples will be converted to a 1024 voltage level. What's that means? Can anyone tell me? What is this mean? You can't pin, no? How I tell you? Okay. So you can't anything. You can't see my writing. Okay. Can you see? I think in the top of the screen you can see my. In the top of the screen you can see my name. No. Nuannathanayake guest. There I have turned on the camera. No, that cannot be happen. You should. So you are using a phone or laptop? Yeah. Maybe if it is a mobile phone, please slide your screen. Then you can see the tabs. Okay. If you slide your mobile phone screen, you can see some tabs. The participant list as a tab. Okay. Each participant has one tab. Can you see that one? And now you can see, no? Yeah. Now you can see, no? So if you are using the phone, please slide your screen, then you can see the participant list. Okay. Then there is a tab called one Attanayaka guest. Click on it and make it pin. Then you can see the screen. I think now it is okay, no? Okay. So what is this means? Can you tell me what is this means? So it means that this sample, any sample, okay? So if I write, okay, so this will be the analog signal and I sample it, okay, and I will get some sample like this, okay. I will get some sample like this, no, okay. So actually this will be our discrete time signal, no, okay. So this will be our continuous time signal and this will be a discrete time signal, okay. So it said that this sample, any sample will be quantized into 1024 levels, voltage levels. I think this 1024 level is very famous one. Okay. Anything comes to your mind? Okay, it means that, okay, it means that in this ADC, for this ADC, okay, for this ADC, it can support 1024 voltage level, okay, voltage level. For example, if you get, say this signal, say this signal is +5 and with -5 maximum peak to peak value, +5 and -5, okay. So your maximum voltage will be -5 to +5, okay. And this voltage level, so there are 10 around, the different is 10 volt, okay. So this voltage level you can divide into 2024 levels, okay. Okay, and each level can be represented using binary data, ones and zero, okay. So each this level can be represented using binary value, binary sequence like this, okay. So if there are 1024 levels are there, okay, how many bits you need to represent this voltage level, one voltage level? Can anyone tell me? Okay, so there are, yes. So another one, can anyone tell? So there are 1024 voltage levels, okay, voltage levels, okay, 1024 voltage levels, okay. So if you want to represent one voltage level, okay, if you want to represent one voltage level, how many bits you want? That is 10, no? Okay, so I think one or two have given the answers, okay. So you know that 2 to the power 10, it will be 1024, okay. So if there are 1024 voltage level, this voltage level, okay, 1024 voltage level, and if you have 10 bits for all one voltage level, you can represent every voltage level, okay. So what is this 10 means? What is this 10? What is this value? Actually, in if you are by ADC, this value is given, okay. So what is this called? Can anyone tell? What is this value called? It is the resolution of the ADC, no? It is the resolution of the ADC, okay. So resolution means one voltage level, okay. Resolution means how many bits we are using, that ADC, specific ADC is using to represent one voltage level, okay. Here it is 10 bits, okay, 10 bits, and we can represent 10 to the 2 to the power 10 voltage level, that means 2024 levels you can specify within this ADC. Okay. Okay. So now, okay, if you consider this ADC, okay, for that one sample, I will write. I forgot that one. Okay, one sample. For one sample, how many bits it need? For one sample, how many bits it need? It is already given. That is the resolution. How many bits? 10 bits, no? So in this AD, one sample will be represented using 10 bits. Okay. I think you can get the idea. Okay, one sample will be represented using 10 bits. Okay, that is the resolution of the ADC. Okay, so what is the first question? So that is the information related with this communication line and the ADC. Okay, so let me check the. Okay. So our first question is, what is the sampling frequency and folding frequency? Okay. So our first question is, what is sampling frequency? What is sampling frequency? Okay. Okay. So we are not, you can see that here, if you go to this question, you can see that we are not given any sampling frequency or sampling time. Okay, sampling frequency or sampling time we are not given. Okay, so this question asks us to verify or asks us to find what is the sampling frequency related with this communication line. Okay, so that is you should understand. Okay, so what is the sampling frequency related with this transmission line? Okay, so I think we have enough data to calculate that one. Okay, so what is sampling frequency actually? Can someone tell me what is sampling frequency? Sampling frequency means if you in a simple way, if you tell what is that? Sampling frequency means number of samples, no? Number of samples per 1 second. Is this okay? This is the sampling frequency, no? Am I right? So this one sample is related with one cycle actually. Okay. One sample is related with one cycle. So sampling frequency is number of samples per 1 second. Is it okay? So if you have any problem, please stop me and you can ask any question. Okay. So that is the number of samples per second, that is sampling rate. Okay. So related with this communication line, how many samples can it carry per 1 second? That is the sampling frequency, no? Okay. So with this transmission line, how many samples we can send to this communication line per 1 second? How many samples? We can send 10,000 bits. No, within 1 second, you can send 10,000 bits. Okay. Within 1 second, you can send 10,000 bits. That is given. Okay. But one sample need 10 bits. Okay. So one sample need 10 bits. Okay. So for 1 second, you will send 1,000 samples. No? 1,000 samples. Is this okay? Okay. So you can see that, okay, one sample, we have 10 bits. For one sample, we have 10 bits. Okay. In other way, 10 bits is one sample. 10 bit is one sample. So here you have 10,000 bit. Okay. So 10 bit is one sample. Okay. Then 10,000 bit. 10,000 bit means you have to multiply this 1,000. No? You have to multiply this 1,000 and you have to multiply this way also by 1,000. Okay. So 10,000 bit means, okay, 10,000 bit means 1,000 sample. Am I right? Okay. 10 bits, one sample, 10,000 bits, 1,000 sample. Correct? Okay. So for 1 second, 1,000 samples can be sent. Okay. That is the sampling frequency. Okay. So the sampling frequency is related with this. Related with this. I mute. So mic is turned on. So I have muted it. Okay. So related with this communication line, okay, so it is 10,000 bit per second, okay, bit per second, okay. So you can send, okay, you can send 10,000 sample, 10,000 sample per 1 second, okay. That means your sampling frequencies, okay, sampling frequency, 10,000 sample per second. Sampling frequency means number of sample per second. That is 10,000, 10,000, sorry, not 10,000, 1,000 sample per second. Okay. So this will be your sampling frequency. Okay. And I think you can also write this using hertz. Okay. Using hertz. Always 1 by second is hertz, no? 1 by second is hertz. Okay. And also you can write this in terms of hertz, units, that is 1,000 hertz. Okay. That means one sample is related with one cycle. Okay. So this will be your sampling frequency in hertz, and this will be your sampling frequency in sample per second. Okay. Both are correct. Okay. So are you okay with this? Anyone have any problem?
Nuan, just to interrupt you. So just to aware this basic process.
Okay.
Now the idea is actually we have a continuous time signal and we want to transmit it through a kind of a digital channel. So then, as you simply highlighted, we need a kind of a unit called ADC, analog to digital converter.
Yes, sir.
So the analog to digital converter, we have mainly 3 blocks, internal blocks. One is the sampler, which basically convert this continuous time signals to a kind of a discrete set of samples. So the continuous time signal is converted into a discrete set of samples through the sampler. So then once we get the series of these discrete samples, we can feed it to the quantizer. So the quantizer means, so like for example, if you have, as Nuan drawn in his paper, so we'll get this discrete set of samples. So then you can think of the span of this samples. So by looking at this discrete set of samples, you can see what would be the maximum peak of the samples we can obtain, and what would be the minimum value of the samples we can obtain. Because like once you do the sampling, so we will ended up with a simple discrete set of values. Those are the samples. So then depending on the span, so the maximum and minimum, we can decide what would be the best quantizing level. So how many bits
Sorry, excuse me.
actually, yeah.
Sorry, shall I give you the screen sharing?
Is it possible?
Yeah,
Yeah.
yeah.
If it is the case, so then I can share it. I'm just adding some comments because like, so then I feel like, so this discussion would be the last session we planned before the exam.
Yes. So I think now you can share the screen.
Yes, thanks. Yes. Hope you can see my screen.
Yes, sir, we can see.
Yeah, so the concept is actually like we have this kind of a signal. So this is our XAT. This is the continuous time signal. So according to this given signal, so you can simply pick that. So this is a kind of a signal comprises of two different frequencies. Like one is having this 605T and the other one is having this 1805T. So by looking at this format of the signal, you can immediately pick that. So this analog signal or the continuous time signal is having two different frequencies. Okay, so this is your continuous signal. So once you fed it to the sampler, so this is your sampler. So then we'll end up with this kind of a discrete set of samples. Okay, so once you get this set of samples, you can decide what would be the peak values. Like let's assume this gives the peak, positive peak, and let's assume this gives the negative peak. So then by looking at this, the entire span, so we can think of a kind of a quantization level. Quantization means like we can either equally partition this entire span, either we can, so we can partition it to a kind of a equal space blocks, or else in certain cases, so we can have a kind of a non-linear type of type of a quantization. So then, like for example, if the samples are basically like this, so then we can simply see that so all these peaks are basically lie on this region. So one or two samples may be here. So then we don't need to have a kind of a linear quantizer, which means like we don't need to split this entire span into equal spaces. No need to have these equal spaces. Because like a very few samples are lying this here, this region, and most of the samples are in this region. So then we can have a kind of a nonlinear quantizer where we have a higher precision during this region and lower precision during this region. So it means like during this blue shaded area, yellow shaded area, we can have higher number of quantization levels like this. So then the difference between two consecutive levels is very small. Here you can have this kind of a higher quantized spacing. So everything depends on the distribution of the samples. So this is basically a kind of a quantizer having equal space levels. So these are the levels that Nuan mentioned. So according to that, so they want to quantize this voltage block. So these each and every sample represent a kind of a voltage value in this continuous signal. Okay, so then they need 1024 levels to represent these, which means like if you take the log 2 of this value, so you can simply say that each sample can be basically represented using 10 bits, because this is a binary coded one. So that's why we took log to the power 2. So if it is the other some other order, so then you can have this log to the power n. So this is a binary coded word. So it means like we can have two stages, ones and zeros. So then you can simply take the log inverse or log to the power 2 of this 1024, which equals to 10, which means like each and every sample is basically coded with 10 bits. Like so then once you split this entire space into 1024 levels, you can basically approximate each and every sample to the neighboring quantization level. So then we can have a coding like the the first quantization level is having 10 zeros. So the next quantization level is having 9 zeros and 1. So then the other one is 8 zeros, then 1 0, then 8 zeros, 1 1. Likewise, you can have this up to 10 ones. Okay, so these are the quantization level, and we assign a kind of a binary coding for each and every quantization level. So then we can approximate these samples to the neighboring quantization level, and the corresponding binary code can be picked from this table. If it is close to the 0 line, so you can just code it as zeros, 10 zeros. If it is, if this sample is very close to the very first quantization level, you can simply code it as 9 zeros and a 1. So likewise, we can simply convert this continuous signal to a kind of a binary coded word. Okay. So then keep in mind, so the Nyquist frequency or the Nyquist rate is basically linked to the continuous time signal. Depending on the properties of this continuous time signal, you can simply calculate what would be the Nyquist sampling rate. But the sampling is up to you. You can decide a kind of a suitable sampling frequency and do the sampling. So it's under your control. But if you really want to reconstruct it, as we discussed during the previous session, so whatever the sampling frequency you select should not have this aliasing effect. If you basically select a proper sampling frequency without having this aliasing, you can reconstruct the original signal. So the sampling frequency is the one you select at a sampler, but the Nyquist rate is a kind of a property coming from the continuous time signal. So you can see this difference once this one is described in the next answer for the next question. Yes, go ahead, Mohan.
Thank you, sir. I think that explanation will be useful when we are doing the other questions also. Thank you, sir. So I think you can see my screen now, no? Again. And anyone feedback? Can you see my screen? Can you see my camera? Okay, thank you. Okay, thank you. So now we are asked to find the fold-in frequency. Okay, fold-in frequency. Sometime you may not come across with this fold-in frequency. Okay, I'm not sure. Okay, but anyway, it is very simple. Folding frequency is always half of the sampling frequency. Okay, folding frequency is always equal to the half of the sampling frequency. This folding frequency we need actually to verify the Eliasing effect. Okay, so in the next, I think in mid exam or assignment 1, you have to use this theory, okay, to do one question. Okay, so we will try to do that one. Okay, okay. So so up to this level, you can keep remember that the folding frequency is the half of sampling frequency. Okay, so in this case, our sampling frequency is 1000 hertz. Okay, so the folding frequency, let's say it is FA, it is equal to Fs by 2, that is 500 hertz. Okay, 500 hertz. Okay, so that is the answers for the first question. Okay, let's go to the B, the second question. Okay, and now we are given a signal. Okay, we are given a signal that is, I think you can see my screen, XAT equal to 3 cos 600, so 605t plus 2 cos 1005t. Okay, so this is a composite signal. No, we have two signal. Okay, I think you can see that one. 3 cos 605t, okay, plus 2 cos 1805t. Okay, so this is a composite signal. Okay, we have two cost terms. We have collection of two cost terms. Okay, so in other words, we have two frequency components. Okay, here we have two frequency components. So with this signal, okay, we have two frequency component. Okay, two frequency component. So that is, it is a composite signal. Okay, two frequency component. Okay, I think we have seen this kind of signal in MATLAB. Okay, so you can see that if the frequencies are changed, okay, that will not a sinusoidal signal. Okay, but the frequencies are same, again, that will again generate a sinusoidal signal. Okay, and also we have sampled this composite signal. Okay, and we have seen the MATLAB demonstration also. Okay, so if you want to sample this, okay, so you can see that there are two frequency components. Okay, there are two frequency components. So if I write the two frequency component, okay, let's say that this is F1 and let's say this is F2. Okay, so if I write the frequency component, okay, so this is 605 is the angular frequency, no, that is omega. Omega 1 is 605. Okay, and if you want to find the F1, that is 25 F1. Okay, so that is equal to 605. That means 1 is equal to 300, no, 300 hertz. Okay, so this is our first frequency component, that is 300 hertz. Okay, if it is radian per second, that is 605 radian per second. Okay, so this is the angular frequency. The both are same. Okay, both are correct. Okay, you can given the answer from the angular frequency, or you can give the answer in normal frequency in hertz also. Okay, so both are correct. Okay, so if you consider this one, okay, so let's say that omega 2, okay, that is 1805. Okay, so F2 will be, this should be divided by 25, no? So 5 cancel out and you will get 900 hertz. Okay, so this will be your second frequency. Okay, so this is the first frequency and this is the second frequency. Okay, now we are asked to find the Nyquist rate. Okay, now we are asked to find the Nyquist rate for this X80. Okay, so what is the Nyquist rate for this X80? Can someone tell me? Okay, no. Yeah. Yeah. So others, what about others? I think you should know. Yes, I think most answers are correct. Okay. So Nyquist, I think you know the Nyquist theorem. Okay. It said that our sampling frequency, okay, sampling frequency should be greater than or equal to the signal frequency. Okay, signal frequency. Okay, let's say that it is FM or something. Okay. So this is in order to avoid aliasing. Okay, this in order to avoid aliasing. Okay, aliasing. Okay, so this sampling rate is given to avoid aliasing. Okay, so in this signal we have two frequency components, F1 and F2. Okay, F1 and F2, and you can see that F2 is the highest one. F2 is the highest frequency, that is 900 hertz. Okay, so if you select the sampling frequency greater than, sorry, this should be twice. Okay, I'm sorry, the Nyquist theorem is Fs should be greater than twice the signal frequency. Okay, yeah, thank you. Okay, thank you, Ahmad. Okay, okay, so so if you get if you select your sampling frequency greater than twice of this highest frequency, so it will not create any problem, no? Otherwise, if you select this one, the your lowest one, and if you get the twice of that sampling frequency, that is not enough to sample this frequency component. Okay, that is not enough to sample this one. You will get aliasing effect. Okay, so your sampling Nyquist rate will be Fs should be 2 F2, that is maximum of the maximum frequency component. Okay, so your Fs will be 1800 hertz. Okay, so this will be your sampling frequency. Okay, I think we have seen this in MATLAB also. Okay, so we can see that when we have sampled the signal with 600 hertz sampling rate, okay, we can't reconstruct the signal. Okay, so we will get another signal that is not the correct signal. Okay, so we have demonstrated this in MATLAB, and I think you have the idea. Okay, so this will be our sampling frequency. Sorry, Nyquist frequency. Nyquist sampling frequency. Okay. So now we have C. Okay. Okay. So the part C asks what are the
one small interruption. So
yes,
just to edit your stuff. So keep in mind, if it is a cosine or a sinusoidal signal, always, so this signal basically like a xt, so this should be basically modeled as a cos or sine omega t, or else we can simply say that a cos 2 phi ft. So this is the generic model of the cosine or a sinusoidal signal. If it is a cos function or a sinusoidal, so it should follow this format. So in this first case, so this omega is the angular frequency as Nuan highlighted. So in the second case, this F is basically the frequency of the signal in hertz. So the omega is the angular frequency in radians per second. So F is the frequency of real frequency of the signal in hertz. So if you are given a kind of a signal trigonometric function based on the trigonometric functions, always try to fit it into this standard form. So then you can either extract this omega of the signal, angular frequency, or simply you can extract the frequency of the signal. Okay, so if you just refer this given signal, so one is actually cos 605t. So if you simply plug into the model which we discussed here, so it's like cos 25 into 300t. So then you can immediately extract the frequency of the signal. So it's actually 300. So similarly, you can apply the same concept to the next one as well. And if it is a composite signal, which means like a combination, the signal is a kind of a combination of these multiple frequencies. So then the Nyquist rate is linked to the maximum frequency of the composite signal. Maximum frequency. So as Nuan correctly highlighted, so the maximum frequency of this given composite signal is 900 Hertz. So then you can easily calculate the Nyquist sampling rate based on the maximum frequency component of this composite signal. So if you just sample the signal with a below rate, so then definitely the highest frequency component would be alias with any kind of a signal. So that's why we want to avoid that. So that's why we basically pick the maximum frequency component of the signal. So, as Nuan highlighted, pick 900 as the maximum frequency, and the Nyquist would be the 2 times that frequency. Okay. So this is the standard form. So you can basically model your given signal for this cosine form. Then you can either extract the radians per second, which is the angular frequency, or the real frequency immediately. Yes, thank you, Nuan. Go ahead.
Thank you, sir. I think you can see the screen again. Okay. Thank you, sir, for your explanation again. So I think you have get the idea about that one very clearly. Okay. And one student has asked that what happen if we have sine and cos terms. Okay. So you can see that if you have a sine, okay, sine, that means only a phase shift cos signal, no? Okay. For example, you can write any sinusoidal signal, okay, with the phase component also. Okay. So that sine signal is, you can convert again into a cos signal using a phase shift. Okay. If you add the phase shift, it will be a sine signal. Okay. For example, if you get sine theta by 5, again it will be a cos. Okay. Cos theta. Okay. So you can add a phase shift and convert. Okay. So when you are finding the sampling rate, you have to only concern the frequency component. Okay. So this frequency component, if this for the signal, the frequency component is the angular frequency component is 605. Okay. And for this one, it is 1805. Okay. So that is the frequency component. So you have to only concern on this frequency component. Okay. So if, for example, if you have sine signal, okay. So if this xat is given as 3 sine 605t plus 2 cos 1005t, okay. So again, the frequency component will be 605, okay. The frequency component will not change, okay. So it will be 605, okay. So for the, if you get sine or cosine terms, you have only concern about this omega, okay. Only you should concern about this omega or 25f, okay. So these are the frequency related components, okay. So is that clarify your question?
And a small addition, and one.
Yes.
Like for calculating the Nyquist rate, yes. So there won't be any different whether the combination is cosines or sines or a mix of cosine and sine.
Yeah.
But as you highlighted here, sinusoidal is a kind of a cosine form shifted by 90 degrees.
Yeah.
Okay, so then the real impact is coming to the discretization. Once you discretize the given signal, so you have different type of discrete signals. If it is like cosine plus cosine, so we will get a kind of a different composite signal. If it is cosine plus sine, so then we have a different composite signal, and if you do the sampling, we can simply see these discrete versions are completely different. But to understand the Nyquist rates and everything, whether this signal is a completely a cosine block or a sine or a kind of a combination of cosines and sine, doesn't matter. We simply want to extract the frequency of the signal. But if it is a kind of, if you are asked to evaluate what would be the discrete signal you are ultimately getting in, so then if you have two cosines and one cosine and one sinusoidal, so the discrete form would be different, because as Nuwan correctly highlighted, so the sinusoidal is a shifted version of cosine. So then you can simply, as Nuwan always promoting MATLAB, so you can just draw this composite signal. If the composite signal is 2 cosine, and what happens to the composite signal if it is a one component is a sinusoid. So you can see that really the generated continuous signal is completely different. So once you do the discretizing, you can see that real effect. But to evaluate this Nyquist and related stuff, so we want to extract the frequency only, so that for that component it won't affect whether it's a sine or cosine. But once you do the discretizing, you can see if you have a kind of a phase shift, so it's really affects to the discrete version. Yes, so that's the one I want to highlight.
Okay, thank you, sir. Shall I proceed, sir? Okay. Yeah, if you have a sine square component, okay, you can again write it as a, so if you have a sine square component, okay, so let's say that sine square theta, okay, so you can so you can write this as cos square theta minus 1, okay. Then again, this cos square theta, you can write it as a cos and sine terms, okay. Cos and sine terms, okay. Cos theta, sine theta by 2, phi by 2, okay. Then I think if it is a
No,
sine,
I think it's easy. We can convert into two cos 2 thetas.
yeah.
So if I remember, for cos 2 theta, we have two versions.
Yeah.
One is with sine squared, the other one is with cos squared.
Yeah.
So you can immediately convert all these square terms of this trigonometric to 2 theta. So then the real frequency is 2 times whatever.
Yeah.
I guess.
Yeah.
So it's I think easy.
Like this way, no, sir. Okay, so
here this 1
yeah.
plus something.
Yeah.
I'm not sure.
So if you get the cos 2 theta, then thank you, sir. Thank you for the reminder. So if you write the cos 2 theta, you can write it as cos square theta minus sin square theta. Okay. Then again, you can write this cos square theta as 1 by 1 minus sin square theta minus sin square theta. Okay. So you have 2 sin square theta. Okay. 1 minus cos 2 theta. Okay. So actually, Dr. Desh, I think sir has mentioned this identity. Okay. So you can see that if you have sine square terms, okay, it will be 1 minus cos 2 theta. Okay. You can see that your theta now is 2 theta. Okay. It is not theta. Okay. So so this 2 theta also you can write, so theta you can write as omega t. That means 2 theta is 2 omega t. Okay. So now your frequency is doubled. Okay. Now your frequency is doubled. Okay. So if you have sine square theta, you can't just get this value. Okay. For example, here if you have 3 sine, if you are given xat as something sine square something to 500 t or something. Okay. This will not your frequency component. Okay. You can't get this frequency component at first. Okay. By looking at this. Okay. You have to write this terms of you have to remove this square value. Okay. And you can use this identity. Sin square theta 1 minus cos 2 theta. So if you write in terms of this, you will get 3 minus 3 cos now 2 theta. That means 4,500 t. Okay. So here you can see that your frequency is changed. Okay. So you can see that if you have sin square component, it will affect to the Nyquist rate. Okay. It will not, if you said that if it is not affected to the Nyquist rate, I think it is wrong. So if you have sin square terms, it will affect to the Nyquist term. So I think I am correct, no?
Yeah. So the simple idea behind this is like if you simply refer the sinusoidal signal. So we have this positive cycle, half cycle, then negative half, then positive, and then negative. No.
Yeah.
So if you make it squared, so these negative halves are simply push into the positive direction. So then automatically the frequency gets double.
Yeah.
Did you get the point?
Yeah, I get the point, sir.
Yeah.
But I don't think.
So
yeah.
What I want to highlight here is this, like if I simply say that. So this is the, let's see, this is your sinusoid. So we have positive, negative, positive, negative. If you do the, the square, so these negative components are basically moved to here. So then if you, this is simply refer this half wave rectification and full wave rectification. So in the full wave rectification, we can model it as 2 times the previous frequency. So here we have this frequency get doubles. Okay, so that's why once you convert the sine squared or cos squared into kind of linear term, so we have the frequencies with the 2 times this original angular frequency in the sine squared or cos squared. And keep in mind, in addition to that, we are getting a DC frequency component, a DC signal as well. The component having a 0 frequency. So if you just replace it with 1 plus cos squared or 1 minus sine squared, so we have one term there. So this is representing a DC signal with a 0 frequency. So keep in mind, so there's a kind of a quantity coming from the 0 frequency as well. Yes, so you are very correct.
Yeah, thank you, sir. I think that question is very good. Okay, I think if you get the multiplication of two signal, you can't say that that is related with the. I think we have seen this in MATLAB. Okay, I have explained this with related to mixture, as I can remember. Okay, for example, if you have a mixture, RF mixture or something. Okay, so this will be your input signal. Okay, some signal, and this will be another signal. It may be generated using a local oscillator or something. So if you get the mixed output, okay, let's say it is ZT, you will get XT into YT. Okay, XT into IT. Okay, so if you are going to sample this one, as I think I can done this in MATLAB also. Okay, if you go through that MATLAB demonstration, you can see this. Okay, so I think you can remember that if you have the multiplication, okay, if you have a multiplication, we have to write in terms of as the collection of cos and sine terms. Okay, so you can use, there are several trigonometric identity. Okay, cos alpha plus beta is equal to something, cos alpha minus beta is equal to something. Okay, so so this may be a cos signal, cos 25 ft or something. This will be a sine signal or cos signal, phi t ft something. Okay, so using this identity, you can, and also there are some identity for sine alpha plus beta, sine alpha minus beta. Okay, so if I write them, it is cos alpha, cos beta minus sine alpha, sine beta. Here it is plus. Okay, the same term plus. And for sine case, you have different sine alpha cos beta plus cos alpha sine beta, and here you have minus. Okay, so if you have sine or cos product, cos or sine product, you can use this identity, and you have to subtract or add. Okay, then you will have sine alpha plus beta plus sine alpha minus beta, like frequency. Okay, we have done this. Okay, I'm just have a recap. Okay, and if you have cos and cos terms, you can use this one identity. Okay, because it has cos and cos term, cos alpha cos beta. So this xt is a cosine and cos signal, and this also a cos signal. You can use this identity. Okay, so it will be cos alpha plus beta plus or minus cos alpha minus beta. Okay, so using this identity, we have to convert this signal into this kind of collection. So here you have a sine and cosine collection. Okay, sum. Okay, as a sum. So you have to convert this multiplication to a sum. Okay, then you can find the, so these are the frequency component. Okay, so these are the frequency component. For example, if you have sine cos alpha and sine beta something signal. Okay, so you will have sine alpha plus beta, sine alpha minus beta. So your frequency will be alpha plus beta or alpha minus beta. Okay, so these are the frequency component. Actually, these are not directly frequency component. Always this is the angle. Okay, so this can be written as omega t. Alpha plus beta is can be written as omega t. So you have to remove this t, and you have to get only this component. So that is your frequency component. Okay, I think we have done this. I think is it clear? So if you have any problem, so I think we have done this kind of signal. Okay, thank you. This kind of signal we have done in MATLAB also. We have sample. Okay. Okay. Thank you for the feedback. And actually, that whole number is the amplitude. Okay, that 3. That means I think Dr. Desh has explained this. So xt can be written as cos 25 ft plus 5 or something. So this 5 is the phase. It will not affected to the, sorry. Okay. So any signal, any sinusoidal signal xt can be represented as x cos 25 ft plus 5. Okay. So you can write this in terms of three sine signal. Okay. And only this phase will be changed. Okay. So this A is the amplitude and phi is the phase. Okay. This is amplitude. This is phase. And this amplitude and phase are not affected to the frequency. Okay. And this part only affected to the frequency. Okay. So this amplitude, that is 3, will not affected to the frequency. Okay. Yeah. If you have this kind of signal, if you have a DC plus DC shifted signal. Okay. So we have seen this one also, like this, cos alpha, cos beta. Okay. Maybe like somewhat like this. Okay. So this is the DC component. Okay. So this is the DC component. And you can see, you know that DC component is like this. So you can assume this DC component is a periodic signal. Okay. And the period is anything. That means the frequency is anything. Okay. So if you get the frequency related with this cost and time terms, it is also valid for this DC component. Okay. So this DC component also will not affected to your Nyquist rate. Okay. Actually, this DC components, when we are talking about the DC components, the Nyquist rate is not applicable. Okay. I think you got it, no? Is it clear? Okay. Okay, thank you. Okay, so we will quickly move. Okay. Otherwise, we are getting out of time. Okay. Now, the one thing you should understand that here we have so we have find the Nyquist rate. Okay, let's say that this is Fn Nyquist rate, Nyquist sampling rate. It is 900. Sorry, 1800 hertz. This is Nyquist rate. Okay, so this rate is required to sample the given XAT. Okay, so this rate should be there to sample this signal. Otherwise, you will end up with Lysine effect. Okay, so if you choose any sampling frequency less than this value, so you will get Lysine effect. Okay, so you have to use at least 1800 hertz in order to avoid the Lysine. Okay. Okay. So now, I think okay. Now okay. Now the third question is, what are the frequencies in resulting discrete time signal? Okay. So you can see that actually that question should be specified. Okay, but here it is not specified. Okay. So you can see that we have two sampling rate. No. So this is the Nyquist sampling rate. This is Nyquist sampling rate. Okay. This is Nyquist sampling rate. And we have found another sampling rate that is related with the ADC and line. Okay. So that is related with ADC plus line, your communication line properties. It is related with your ADC and communication line parameters. So that sampling frequencies, let's say that it is Fs, that is I think 1000 hertz. Okay. So this is the Nyquist rate. Okay, to sample this XAT, and this will be the possible sampling rate. Okay, because this sampling rate is supported by the ADC and line. Okay. Okay. So this question should be specified. Okay, the third question should be specified in which we are going to sample in the frequency. Okay, in which frequency, in which sampling rate we are going to sample in the frequency. Okay, but in practical, you can see that this is the practical possible value. This is the practical possible value we can go. Okay, this is the practical possible value as in the given case. Okay, so I hope the part C is asking the resulting discrete time signal with respect to this 1000 Hertz signal, 1000 Hertz signal, the 1000 Hertz sampling rate. Okay. Okay. So we will see. Okay. I think now, I think you are cleared. No. If you have any problem, you can ask me. Okay. So you can see that first we have calculate the sampling frequency Fs, that is 1100, sorry, 1000 Hertz. Okay, so that is the possible value. Okay, that is the possible value, practical value related with the ADCN line. Okay, so this is the practical value. Okay, and next we have calculated Nyquist sampling rate. Okay, so it said that for sampling that XAT signal, we need 1800 Hertz at least to avoid the aliasing method. Okay, but with this system, we can't achieve this one. Okay, with this system, we can't achieve this one. This can only we can achieve. Okay, so I think number C, asking the question, asking to sample the signal with this frequency, sampling frequency. Okay. So we have XAT. Okay. So we have XAT, this kind of continuous signal. Okay. Then we send this signal through a sampler. Okay. Sampler means it is just like a switch. Okay. You can implement this using a transistor or something. Okay. This sampler you can easily implement. Okay. In electronics. Okay. So this will be some kind of electronic switch. Okay. And on-off frequency of this switch is the sampling frequency Fs. Okay. So if you find the on-off time, it will be Ts. Okay. And that is sampling time at it is equal to 1 by Fs. Okay, I'm not going to explain this because we have already learned these things. Okay, and we have sent this signal to the sample, and you will get the discretized signal like this. Okay, so this will be some kind of analog signal, continuous signal. Okay, and you will get again this kind of discretized signal. Okay, now we are asked to find this discretized signal. Okay, if it is sampling using this Fs in this 1800 frequency. Okay, so if I write the continuous time signal, okay, it is 3 cos, let me check, 3 cos 600 5t plus 2 cos 1805t. Okay, so this will be our discretized, continuous signal, and you have sent this through a sampler, and this T will be changed to N. No? That is our discretized signal. So this is N, number of samples. Okay. So this is number of samples. And we have learned that this number of samples is related with the time. Okay. It is related with time like this. T is equal to N Ts. Okay. So we have learned this one also. Okay. And Again, we can write this in terms of frequency because we are given the frequency. Okay, TS is 1 by Fs. Okay, so you can use this identity and you can write this T is equal to N by Fs. Okay, like this. Okay, so this will be your sampling frequency. Sampling frequency. Okay, so instead of this T, I can directly substitute this value, no? That is the normal way to find the discretized signal. Okay, so I am going to substitute this one. So I will get XAN, that is my discrete time signal. So this is my discretized signal, and it is equal to 3 cos 605. Instead of this T, I will use N by Fs, N by Fs. Okay, so that means I am going to nominalize this frequency by Fs, sampling frequency. Okay, so I think you can remember that we call this as a nominalized frequency. Okay, when we discretize this, that is not same as the original frequency, continuous time frequency. Okay, so it will be a nominalized frequency, and it is nominalized by the sampling frequency. Okay, so this will be this. Okay, and to cos 1805, instead of this T, I can write in Fs. Okay, so this Fs should be 1000. Okay, so if I write this XAN, we have 3 cos, this is 1000. Okay, so I have 0.65 N plus 2 cos, this is 1000, so I have 1.85 N. Okay, so I have this discretized signal. Okay, so is this okay? So this is the answer. Okay, so this is my discretized signal. Okay, simply we can calculate this one. Okay, so this will be my sampled signal. Okay, so we have number of samples N. Okay, okay, now, okay, so so what happened actually? So what do you think? So this what do you think about this signal? Okay, so if you're going to reconstruct this, is it okay or not? Can you tell me, someone? Can please feedback? Are you okay with this discretized signal? Yes, we cannot. Why we cannot? Yeah. So how we can tell that it, so definitely it will apply some aliasing effect. So by looking at the signal, yeah. So by looking at the sampling rate, we can tell. Okay. By looking at the sampling rate, we can tell. Okay. But now, if you don't have the sampling rate, okay, if you don't have the sampling rate, okay, if you say that you don't know the sampling rate, okay, say that you don't know the sampling rate and you have the sampled signal. By looking at the sampled signal, can you get the idea whether this signal can be reconstructed or not? Actually, we can get, okay, we can get, okay. Actually, I have a problem with this terms. Anyone can tell what is, why this is? This is the theory you have learned. Okay, this is related with the theory you have learned previously. So I am not okay with these terms. Can anyone tell why? Why? What is the problem with this term? Can you remember this kind of, I think Dr. Udesh has explained this very well. Okay, I have go through that lecture, okay, to learn this stuff actually, okay. Can you remember this identity? Omega k is equal to omega naught plus 2 5 k, okay. This omega naught should be within -5 and +5, okay. So can you remember this one? I think you have learned, okay. I have gone through this lecture that Udesh has done, okay. I don't know for you, maybe the later batch, okay. I have gone through that lecture, okay. So actually you can see that this omega, okay, okay. So you can see that this omega naught should be within -5 and +5, okay, okay. Otherwise, there are some frequency component that will get that will create the same signal, okay. So you can see that this omega is more than 1, more than 5, it is 1.85, okay. So with this signal you should have this basic omega naught signal, okay. So if you construct this signal, you will end up with this frequency, okay, not with this frequency, okay. So I think this is also I have demonstrated in MATLAB, okay. So if you have time, I think now you don't have time because the exam is very near, but after the exam, if you want to get the idea, you can go through that MATLAB session and you can get a clear idea about that, how that happened, okay. So we have generated several signals, and we have seen that this is also equal to the this kind of another signal, okay. So so here we expect the high frequency signal, but we will end up with the low frequency signal, okay. Our reconstruction will end up with the low frequency signal, okay. So that is the problem actually, okay. So if you, so normally by looking at the signal also, you can say that this will create a Lysin effect and not, okay, by looking at the signal without knowing the sampling rate, but up to some limit, okay, definitely up to some limit, okay. You can't completely guess that, okay, but you can somehow guess it up to some level, okay. So we will see. Okay, so from this frequency, from this identity, we have derived, we are derived that fk is equal to f naught plus kfs, okay. So we have derived this one also, okay. I can't remember the derivation, but this identity also will be very useful when we are analyzing this kind of signal, okay, whether we have lysin or not, okay. So so first of all, okay, first of all you have to find, okay, now forget the things I have mentioned, okay. Now we will come to the question again, okay. So we have xan is equal, if you have any problem you can ask, okay, you can interrupt me and ask, no problem, okay. Xan, it is 3 cos 0.65n plus 2 cos 1.85n, okay. So so this is the signal, discrete signal, okay, and you can write it in terms of frequency, okay. So this is in omega radian per second value, okay. So as Dr. Udesh told you just now, you can convert this to a frequency, the hertz value also, okay. That is 25f, okay. Instead of this omega, we can write 25f. So we have 25. So here it is 0.3 n, okay, and this will be your frequency f1 plus 2 cos. So here you can write this as 25.9 n. Okay, 0.9 n. Okay, like this. Okay, so this will be your second frequency F2. Okay, so we know that our actually folding frequency, so we have learned, I am talking about the frequency, certain frequency, that is folding frequency. Okay, I have told you that folding frequency is equal to fs by 2, sampling frequency is divided by 2, you will get the folding frequency, and in this case folding frequency is 500 hertz. Okay, 500 hertz. Okay, yes, 500 hertz. Okay, so okay, 500 sir. Okay, so if you look at this signal, okay, if you look at this signal, this has 300 hertz. Okay, the frequency of this signal is 300 hertz because this is 25f 300t. Okay, so this is 300 hertz, and for this signal it is 900 hertz. Okay, 900 hertz. Okay, okay, so if you consider this folded frequency, okay, actually it is also related with the Nyquist theorem. Okay, also related with the Nyquist theorem. So if you have frequency component, okay, this folded frequency fa should be greater than or equal to your frequency. Okay, so this is another way of representing Nyquist theorem. Okay, if not, we have some problem. Okay, so you can see that for this signal, okay, for this signal, the cos signal, first the lower frequency component signal. Okay, so let's say that it is f1, so fa is greater than f1, so it is okay, no aliasing effect. Okay, but for the second signal, okay, that is 900 hertz, let's say that is f2. Okay, you can see that folded frequency is greater than, sorry, less than f2, because your folding frequency is 500 hertz. Okay, it is 500 hertz, and your f2 is 900 hertz. Okay, so it is less than the folding frequency, then you will have a problem. Okay, so you can use you can actually use this formula to check. So definitely this signal will effect, will have aliasing effect. Okay, so this signal definitely will have aliasing effect. Okay, so you can check that this component, what are the aliasing frequency, with what frequency it will affect to the aliasing frequency using this identity. Okay, so it is not in this it is not asked to for this question, but I have seen that in assignment 1 or assignment in your mid semester exam, you have to use this identity. Okay, so these are in your notebook. Okay, this is in your given note, you have this identity. Okay, and also using this identity, there are many questions solved. Okay, so if you have gone through this your note, okay, this you can you should come across with this identity. Okay, so now you can see that our frequency is 900. Okay, so our frequency is 900. Okay, so fk, okay, so you can see that now it is 0.9. Okay, so I think it will take some time. Okay, that is not good actually. Okay, so if you convert this this identity omega k omega naught to 5k, you will get Fk is equal to F naught plus K. Okay, and the the limits for F naught is minus half and plus half, because it is within -5 and +5. No? So omega is equal to 5f. So you have to divide this by 25 if you are going to represent this omega in f. Okay. So f naught, it is minus half and plus half. Okay. So you can see that this f2 is greater than plus half. Okay. Plus half. So there should be f naught value. Okay. There should be f naught value. Okay. So that f naught value you can find using this identity. Okay. So you have fk f naught plus kfs. Okay. So your fs is fk is 900 kilohertz. Okay. F naught, you know, you don't know. Okay. So you can first apply k is equal to 1. Okay. Then you have fs. Your fs is 500. Okay. 500, and you will have f naught is 400 kilohertz. Okay. Sorry, 400 hertz. No, sorry, 400 hertz. Okay. 400 hertz. Okay. Are you okay with this? So fk is 900 because you will have some higher value, fk value. Okay. So it is 900 plus f naught. So you are going to find the f naught. Okay. The lower frequency value, and you will have 500 H. Okay. So this is your sampling frequency, and you have your f naught as 400 hertz. Okay. So this is actually aliasing frequency. Okay. So if you are going to reconstruct this signal, okay, you are expecting 1805 T was 1805 T, but you will not get the signal. You will get person 400 related this with this 400. That means 805 T signal. Okay, so that is the aliasing effect. So you will not get this signal. You will end up with this 805 T. So that is not correct. Okay, so you have the aliasing effect. So are you clear with this? Maybe not, you are not very much clear about this, but if you have idea, I think that is enough. Okay, please go through that MATLAB sessions, and I think you can get the idea about that very well. Okay. So if you have any problem, you can ask. Okay. So I use only this identity. Okay. I use only this identity. That is that identity is derived from these identities. Okay. Omega k is equal to omega naught plus 25k, and fk is equal to fk equal f naught plus k. Okay. Using this identities, we can derive this one. Okay. And using this one, we can find the aliasing. If you get higher frequency component, okay, we can get the lower aliasing frequency. Okay. Are you clear with this? Okay. Okay. So let me go to the next one. What is the resolution? Okay. So we are asked to find the resolution. Actually, I think this question also have a problem. Okay. So this delta normally denote, if you have gone through the ADC data sheet, okay, ADC data sheet, you can find this delta. Okay. So actually here it is not in discussion, it is not explained. Okay. But this delta is referred to the voltage resolution. This is voltage resolution. Voltage resolution. Okay. So you have the ADC resolution, that is 10 bits. Okay. So that is ADC resolution. So if you have the Arduino at Mega board, okay, in that Arduino at Mega board, you have exactly 10-bit resolution ADC. If you have used that, okay. So this delta is referred to the voltage resolution. So I think this also is described by the Dr. Udesh short while ago. Okay. So for this one, we should be given the maximum voltage range that is supported by the ADC. Otherwise, we can't find this delta. Okay. But here it is not given. Okay. So we have to given the maximum voltage range, peak value that is supported by this specific ADC, analog to digital converter. Okay. So in a normal data sheet, normally it is given. Okay. Let's say that, for example, it is around 0 to 12 volt. Okay. As I can remember, this is the input value for Arduino ADC. Okay, it is from 0 to 12. Okay, actually ADC can't support to the minus value. Okay, so if you have, for example, if you have a signal -2 to +2 level, you have to shift this signal to the plus range. Okay, otherwise you can't send that it through a ADC. You have to shift. Okay, practical. When you are doing the final year project, I think you will come across these things. Okay, so you can easily shift this. Okay, for example, if you have data, the signal generator. Okay, so this is ground line. Okay, so if you give some the shifted value, okay, so if your signal is -2 to +2, if you give the ground +2 volt, okay, so it will be shifted. It is the DC shifted. Okay, so this shifted, so you can give this value using a Zener diode or something. Okay, then it is shifted. Okay, so output will be 0 to 4 volt. Okay, it is not -2 to +2, it will be 0 to 4. Okay, when you are doing the, when you are sending the signal through ADC, you have to do this shifting, DC shifting. Okay, DC offset. Otherwise, the minus circle, minus part will not, you will not get the value for minus part. Okay, so normally you should given the maximum voltage range. Okay, it should be 0 to some value normally in practical way. Okay, but maybe for exam you can given -5 to +5. Okay, that means exactly you have 10 volt difference. Okay, so that 10 volt difference is the important one. Okay, so you may given that kind of, but practically you can't do that. You have to shift it, that -5 to +0. That means 5 will be shifted to 10. Again, you have 0 to 10 voltage. That is the difference will be 10 volt. Okay. Okay. So say that if you are given it is 0 to 12, then you can find the resolution. Actually, it is not very difficult. The resolution should be okay. So this is normally related with the ADC. Okay, so I think these are important. As an engineer, I think this specification are important. Okay, so if possible, please keep this in your mind. Okay, so it will be the Vmax. Okay, the supported Vmax voltage maximum minus Vmin divided by your voltage level. Okay, voltage level. Okay, for example, if the Vmax is 12 and the Vmin is 0, and if you have 1025, you will have some value. Okay, some value. Okay, so this will be the voltage levels that can be supported by the ADC. Okay, so for example, let's say that it is 0.01 volt. Okay, So the next one is 0.02 volt. Next point is 0.03 volt. Next point is 0.4 volt, so on. Okay, and you will get up to 12 volt. Okay, like this. Okay, so if your signal has a voltage level between these two value, that means 0.15, you have to approximate it to this voltage level or to this voltage level. Actually, that is quantizing. That is what Dr. Udesh has explained short while ago. Okay, so this voltage value you are assigning the bit combination. Okay, for example, this voltage value you will assign 10 bits. I don't know what are the bits. And this voltage value you will assign another 10 bits. This voltage value you will assign another 10 bits. So okay, so that is the idea. Okay, okay. So we will quickly move to the other question also. Okay, actually this question is in the mid semester exam or assignment. Okay, so I think 2 or 3 student has sent me mail regarding with this question. That is why I put that. Okay, so I will tell this. Okay, so I think now this one also you can do by yourself. Okay, so you can see that the analog signal contains frequency up to 10 kilohertz. Okay, that means it has several frequency component. Okay, that signal. So analog signal, we don't know. Okay, like this. Okay, so this signal you can represent using the Fourier series representation. You can represent this as a collection of sine or cos term. Okay, and also you can represent as a exponential terms like this. Okay, with AKK. Okay, so these are the frequency component. Okay, these are the frequency component. Okay, so it is said that this kind of composite signal is there, and the highest frequency component, let's say that F max, it is 10 hertz. Okay, and we are asked to find the Nyquist theorem and Nyquist rate. So you know that the Nyquist rate should be twice than the maximum one. So Nyquist will be 20 hertz. That is very clear. Okay, and this one. Okay, now you have to use that identity. Okay, the exact identity what I have given. Okay, so we sample this frequency with the 8 hertz, 8 kilohertz, and what happened to the 5 kilohertz signal. Okay, okay, so in this signal, okay, in this signal also the maximum frequency component is 10 kilohertz. Okay, the maximum frequency component is 10 kilohertz. Okay, but there are some frequency component with lower this 10 kilohertz. Okay, so there can be 5 kilohertz frequency components also. Okay, there can be 5 kilohertz frequency components. Okay, so let's take these component. Okay, so which has 5 kilohertz frequency. Okay, so that may be cos or sine signals. Okay, with 5 kilohertz frequency. Okay, now according to the Nyquist rate, okay, this should be sampled using a 10 kilohertz signal. No, the sample frequency should be 10 kilohertz. It should be twice than this one, 10 kilohertz. Now we are going to sample this using 8 kilohertz signal. Okay, now we are going to sample this using 8 kilohertz. Okay, now the question asks what happened. Definitely you will end up with Lysine. And if you want to find the Lysine frequencies, okay, Lysine frequencies, how you find? You can use that identity. Okay, what is that? Fk is equal to F naught plus S, K Fs. Okay, so you can use this. Okay, so how to use this? Okay, so you have Fk. Okay, your frequency, that is 5 kilohertz. Okay, that is 5 kilohertz. And F naught, so you will get some lower frequency component. Okay, so that is the aliasing. Okay, plus it should be KFS. So here you can put K as 1. What is FS? That is 8 kilohertz. Okay, so your F naught will be minus 3 kilohertz. Okay, so normally if you have minus value, okay, so it will be, when you add it to the cos or sine terms, it will be a minus cos or sine. Okay, so amplitude only will be changed, not the frequency. Okay, so you can consider this as 3 kilohertz. Okay, okay, so actually what happened, this 5 kilohertz signals will be aliasing with 3 kilohertz signal. Okay, for example, if you have a frequency component like this, 255T, okay, and if you have discrete, if you have sampled this using S, that is 8 kilohertz, 8 hertz, you will get a cos 255 N8. Okay, so when you reconstruct this, okay, when you reconstruct the signal using this signal, you will get, you will not get this 255T, you will get this, the lower frequency 253T. Okay, so this will not equal. So that is the aliasing effect. Okay, so did you get that? We don't have much time to explain. Okay, so I think you have the idea how we are finding the aliasing frequency component. Okay, so these are very important when we are dealing with signals in practically. Okay, and the same the same things we are asked to find with the 9 kilohertz. So 9 kilohertz you will get 1 kilohertz. No? Okay, so here now we are for the second question, you are asked this, if this FK is 9 kilohertz, what happened? Okay, so if it is 9, FVC is still 8, so 9 minus 8, you will have F naught. Okay, so can you take? So now it is asking FK is 9 kilohertz. What happened if FK is 9 kilohertz? So you will have aliasing effect. So the aliasing effect will be F naught plus 8. So aliasing frequency will be 1 kilohertz. So your 9 kilohertz signals are aliasing with 1 kilohertz signals. Okay, I think that is enough. Okay, so if you have any problem, you can ask. Okay, so quickly we will move to the next one. Okay, so discrete Fourier transform. Actually, I want to do this one also because I think in your assignment or something, you have to perform the convolution, and some student asking how to perform the convolution. To give idea that I put this question number 2. Okay, I will show that one. I will share. Okay. So this is question number 2. I think you can see the screen. Okay. So we are given 3 signals. Okay. 3 sequence discrete time signals. Okay. So every signal has 1, 2, 3, 4, 5 components. Okay. And so it performed the 5-point DFT. Okay. And after performing the 5-point DFT, it multiplied the signal. Okay, so what it means that, okay, okay, so you have I think you can see my screen now again. Okay, okay, so we are moved to our question 2. Okay, question 2. I'm sorry, I have to go quickly. Okay, otherwise now it is almost time has passed. Okay, so we are given three signal x1 n and x2n and sn. Okay, so we are given three signals. Okay, and we are given a signal called yk. Yk is equal to x1k, x2k. Okay, so this is the yk. Okay, uh, so how this signal is so how how we can get this yk signal? This is the frequency domain signal. Okay, after applying the DFT, we can convert our sound discrete signal into frequency domain discrete signal. Okay, so this will be a frequency domain discrete signal. So how we can get this one? Okay, so we have to first perform the DFT in this x1t. So you can get x1k after performing the DFT. Okay, and you have to perform the DFT here for x2 signal also, and there you will get x2k, the frequency domain signal related with this x2n. Okay, after applying the DFT. Okay, so you can see that here you have five component. So at least you have to apply 5-point DFT. Otherwise, it will not enough to reconstruct the signal. Okay, we have I think I have explained this when we are doing the tutorial. Okay, and I think in your note also it is explained very clearly. Okay, so at least we have to perform the 5-point DFT or more than 5-point DFT. Okay, so this is just like a sampling frequency. Okay, this is when we are dealing with the time domain sampling. Okay, this 5-point is referred to the sampling frequency actually. Okay, so if you have 5 component, at least you have to perform 5-point DFT, otherwise you can't reconstruct. Okay, so if you perform 5-point DFT in xn, you will get x1k. If you perform 5-point DFT in x2n, you will get x2k. Okay, and if you multiply them, you will get yk. Okay, now we are asked to find the yn. Okay, that is our first question. We are asked to find the yn. Okay, so how to find the yn? Okay, so one way is to, you can convert this xn into xk, performing the DFT, and x2 into x2k, performing the DFT, and you can multiply the both sequence. Then you can have the ik, yk. Then if you apply the inverse discrete Fourier transform, you will get the yn. You can go in that way. Okay, but it is very long method. Okay, to find the answer, we can use one property. Okay, we can use one property. Actually, that is convolution property. Convolution property of the DFT. Convolution property. Okay, so what is convolution property set? Okay, it is not related with the frequency domain signal only. Okay, it is also applicable for the Z domain also. If it is a complex plane or frequency domain, complex domain or frequency domain, in both cases that convolution property can be applied. What is it said that? It is said that if you have if you convert two time domain frequency, if you convert two time domains frequency x1 and x2n, okay, and if you are going to the frequency domain, this convolution will be a multiplication. Okay, so yk will be x1k x2k. And also in Z domain also we have learned this. This is same, no? In Z domain also, this is this will be a multiplication. X1 is at x2 is at. Okay. Okay. So this property you can use to find the yn. Okay. So we have x1 product x2. Okay. So we are not given the DFT signal, frequency domain signal. We are given the time domain signal. So we have x1n and we have x2n. If you convolve these two signals together, okay, you will get yn. Okay. So you can find the yn by convolve. Okay. So how to convolve? Okay. So I think you can use the matrix method very easily. Okay. You can use the matrix method to find the convolution. Okay. So with related to DFT, you have to find the circular convolution. Okay. So this is applicable to the circular convolution. Okay. Okay, we will see. Okay. So I will write the two sequence. Okay. Okay. So my x1 n will be, I think if you can do this with me, I think it is better. Okay. Those who are not familiar with this, okay, because I think 2 or 3 student has sent me. Okay. So this is 0, 1, 2, 3, 4. This is 0, 1, 0, 0. Okay. And we have to find the convolution. Okay. So how to find the convolution using the matrix method? Okay. Please keep remember that. I think the standard way is you have to write the circle. No, you have to write the bigger circle and smaller circle. Okay. And in a bigger circle, you can you have to divide this the equal section of this circle. Okay. And you have to put the
this value. Okay. Just because you have aced your examinations and graduated.
Okay. I have muted. Okay. So so you can write one signal in anti-clock direction or clock direction. If you are writing in anti-clock direction, so this is x1n. Okay. So you have to get x2 minus n, the time reverse signal. So it will be clock direction. Okay. And you have to find the all related related samples and you have to add them. Okay. Then you have to, so here you are going to you have anti-clock direction. Okay. Now you have to shift it by 1 to the clock direction, and again you have to do that same multiplication and addition, and you have to find the next value. So you can find the next value. Okay. So that is the normal way to find the circular convolution. Okay. But very easily we can find the circular convolution using the matrix method. Okay. So I will explain. Okay. If you are not familiar with this, please adhere the procedure. Okay. Okay. First you have to write, you can select any signal. Okay. You can select any signal and the both signal should be in the same length. Okay. That is the first requirement. Okay. Both signal should be in same length. Okay. What happen if it is not in same length? Okay. What we have to do? We can put zeros. Okay. After the signal, we can put zeros and we can make the both signal in same length. Okay. It is called zero padded. No? it is called zero padded. Okay, so you can add some zero. For example, if you are given one signal with 4 component, okay, and other signal with 3 component, okay, so here 1 and here 3, okay, so this 3 should be also should make 4, so you can simply add 1 0 after the sequence. Okay, so that is zero pad. Okay, so now we no need to do the zero padding. Okay, because the same both length both signals are in same length. Is it clear for you? Any problem with this zero padded, with this zero padding? I think this is also this is very popular now in data when we are doing that data network related things. Also, we are doing this. Okay, to find the Hamming codes and those things. Yeah, we are this zero padding is very popular one. Okay, so in all are okay with this zero padding. If your signals are not in same length, you have to pad, you have to put some zero after the short sequence. Okay, and you can make the both sequence equal. Okay, that is zero padding. Okay. Now I select this one, the first signal. Okay, and if I'm going to make a matrix using this first signal. How I use the matrix? First, I have to write all terms so here it is in horizontal direction. Now I am going to write all these component in vertical direction. 0, 1, 2, 3, 4. Okay. Okay. Now after that, this one also I have to write here. Okay. To that one, this one, the last component, I have to shift to the top. Okay, so the next row, next column will start with 4. Okay, will start with 4 and other are shifting. Okay, so you have 0, 1, 2, 3. Okay, here again 3 I put I get onto the top. This is not minus sign. Okay, here 4, 3, 4, 0, 1, 2, 3. This is not a sign. Okay, so this 3 also I get to upper. Okay, and we have 3, so I have shifted this by 1, 4, 0, 1, 2. Now 2 I get to the top. Now we have 3, 4, 0, 1. Now I have get 1 to the top. Then I have 1, 2, 3, 4, 0. When I get to this 0 here, I will have 0, 1, 2, 3, 4. So that is the same one. Okay. So I will not write this column. Okay. I will stop here. Okay. So I have this one. Okay. And then I have write my second signal. Okay. 0, 1, 0, 0, 0. Now I am going to multiply these two matrix. Okay, so I think can you remember the matrix multiplication? Okay, so matrix multiplication is very simple. Okay, so if you have two matrix, okay, okay, let's say that is 4 by 3 matrix. Okay, so this 4 is row. Okay, 4 is row. So you have 4 rows and 3 columns. 1, 2, 3. Okay. And this matrix should be 3, starting from 3. That means here you have 3 columns. Okay. The next matrix should have the rows equal to this matrix. Okay. So this matrix should have 3 rows. Okay. That is equal to the column of the first matrix. Otherwise, you can't perform the matrix multiplication. Okay, you are going to do the dot product. Okay, so if you please type on it in internet, in Google, you can type it matrix multiplication, then you can get, okay, the details. Okay. So your columns can be anything. Okay, column can be anything, 5, 6, or okay, and finally you will end up with 4 by 6 matrix. Okay, so these 3 cancel out, you will end up with 4 by 6 matrix. Okay, so that means this matrix will define the number of rows, and the second matrix will define the number of columns. Okay, so how to perform the multiplication? So this will specify the row, and this will specify the column. Okay, so first row, first column will be, you have to multiply all the first column with the first row. No, sorry, first row with the first column. Then second row with second column. Sorry, first row with first column, and you can add all the value together. Then you can get the first value, first row, first column value. Then if you multiply first row with the second column, you will have first row, the second value, you have to add all the value together. Then third, first row with the third column, you will get some value. Okay, so on you have to find. Okay, then you will come to the next row, so it will define the row. Okay, now this row will multiply by this column, you will get some value. Okay, you have to add them, multiply and add them. Okay, then this row you have to multiply by the second column, likewise you will get. Okay, so that is the normal way to perform the matrix multiplication. Okay, so that information is not enough. Okay, please refer the Google or your maths book, then you can find. Okay, so we will do this one. Okay, I will do this one. So you can see that for this matrix, now the condition is okay. Okay, so this has 1, 2, 3, 4, 5 columns and 1, 2, 3, 4, 5 rows. Okay, so you have 5 by 5 matrix. Okay, so 5 rows, 1, 2, 3, 4, 5 rows, and you have 5 columns also, 1, 2, 3, 4, 5 columns. Okay, and you have your next matrix is, you have one row, you have one row, sorry, you have 5 rows. Okay, you have 5 rows, 1, 2, 3, 4, 5 rows, but 1 column, you have 1 column. Okay, you can see that here number of columns is equal to the number of rows. Okay, so you can perform the matrix multiplication. Okay, and you will end up with 5 by 1 matrix. Okay, 5 by 1 matrix. Okay, so how to perform that? Very easily you can perform that. Okay, so we will get the first row, and it is multiplied by the first column. Okay, so what happened? 0 is multiplied by 0, we have 0, and you have to plus 4 is multiplied by 1, so you have 4, and 3 is multiplied by 0, you have 0. 2 is multiplied by 0, 2 is multiplied by 0 means this 0. Okay, so 0 is multiplied by this 0, 4 is multiplied by this one, 3 is multiplied by this one, 2 is multiplied by this one, 1 is multiplied by this 0. Okay, so all you will get 0. No, 1, 2, 3, 4, 5 zeros. Okay, so you will have only 4. Okay, you will have only 4. Okay, so that is the value 4. Okay, so that is the first column value, first row value. Okay, and you go to the next one. Okay, then you have to multiply, sorry, this one, 1 by 0, you will have 0, 0 by 1, you will have 0, 4 by 0, you will have 0. 3 by 0, you will have 0. 2 by 0, you will have 0. So you will get 0. That is your next row. Okay. And third one, this one. Sorry, this one. So 2 should be multiplied by 0, 0. 1 should be multiplied by 1. You will get 1. Okay. And others are 0, no? 0 by 0, 4 by 0, 3 by 0. All are 0. So you will have 1. If you add them together, you will have 1. Okay. And next one. So you have 3 by 0 plus 2 by 1. That is 2 plus 1 by 0, 0, 0 by 0 plus 0 plus 0. So you have 0 plus 2 plus 0, 0, 0. So your value will be 2. Okay, and here, next one, you can go to next one. So 4 by 0, 0 plus 3 by 1, 1 plus 2 by 0, 0 plus 1 by 0, 0 plus 0 by 0, 0. So if you add them together, you will have only 3. Okay, so this is the resultant matrix you will get. Okay, so here you will get 4, 0, 1, 2, 3. You can see that it is a 5 by 1 matrix. You have 1 column and 5 rows. 1, 2, 3, 4, 5. Okay, so this is the YN. So this is the YN. So that is how you are performing the circular convolution. Okay, is that clear? Is that clear? Okay, so if you can give me a feedback, it is very helpful. Okay, so I think you have to do this one and you have to perform this kind of circular. Okay, thank you. Okay, so you have to do this kind of convolution. Okay, thank you. Okay, I think you have done this for your mid-semester exam or assignment. Okay, so I think now you are familiar with this. I think 2 or 3 student has sent me a mail. Okay, that is why I put this question, but it is very easy. Okay, so we will go to the next one. Okay, so for a while I will share. Okay, so in next one, so that is somewhat difficult. Okay, but it is not much difficult, but you have to do some more calculation. Okay, so you can see that now, is there any sequence x3 such that xk is equal to x1 x3k? Okay, so I write the s1 also, sn also here, that is 1 0 0 0 0 something. Okay, so now sk x1k x3k. Okay, no, I think that is not much difficult. Okay, we can do that. Okay, so now our question is, okay, we are asked to find any x3. Okay, that means if you have multiplied x1k with another matrix x3k, you should have this Sn DFT value, that is Sk. Okay, so if you go back to time domain, that means you will get Sn. Okay, you will get Xn if you get the convolution of Xn and another unknown matrix, another unknown sequence X3n. Okay, and you are asked to find this unknown sequence. We don't know that sequence. Okay, so they asked to find any sequence. Okay, so that sequence is convolved with x1. You will get convolved means circular convolved with x1. You will get Sn. Okay, so how to do that now? Okay, so we know that we have x1n. X1n is 0 1 2 3 4. Okay. And x3n we don't know. Okay, we don't know the value. But x3 should have the same component. Otherwise, so here you have 5 components. X3 also should have the 5 components. Otherwise, you can't find the circular convolution. So this should have 5 components. Let's put that A, B, C, D, E. Okay. So likewise, it may have some components A, B, C, D, E, F, O, like this. Okay. And now we have to perform the circular convolution for these 2 signals. Okay, how to perform the circular convolution? So very easily you can do that. Okay, so you can use the matrix method. In the same manner, you can use the matrix method. Okay, you can use the matrix method. Okay, so you have x1 name 0, 1, 2, 3, 4. Okay, x2 and you don't know what is. Okay, so we will make the x1 name matrix. So how to create it? Okay, so first you have to write all terms in vertically 0, 1, 2, 3, 4. Then you have to push this bottom one to the top one. Then you push this by 1, shift this by 1. So you will have 0, 1, 2, 3. Same manner 3, 4, 0, 1, 2, 2, 3, 4, 0, 1, 1, 2, 3, 4, 0. And if you get this, push this one, you will get 0, 1, 2, 3, 4. That is equal to the first column. So you will stop here. Okay, so this is your x1 matrix. And you have the x2 matrix, that is A, B, C, D, E. Okay, after multiplying these two, you should get Sn, this one. Okay, you will get this one. So what is that one? This one. You should have this one. Okay, so as a result, you should have S1. So it will be 1, 0, 0, 0, 0. Okay, so you have nice matrix. Okay, now you have to solve this and find the A, B, C, D, E, F. Okay, so very easily you can do that. Not easy actually, because it is very easy. Okay, so how to do this? Okay, so you can find the resultant matrix here, and you can compare it with this one. Okay, then you can find this ABCD value. Then you can try to find this ABCD value. Okay, let's try to do that. Okay, so in the same manner, now I am going to multiply this here. This one is 5 by 5 matrix, and this is 5 by 1 matrix. Okay, and this is 5 by 1 matrix. Okay, so I am going to multiply these two together. Okay, I'm going to multiply these two. So what is the procedure? So this is the column, and this is the row, and this is the column. Okay, so I get the first row. Okay, so 0 is multiplied by A, so you have 0. 4 is multiplied by B, 4B. 3C, 2D plus E. Okay, so you will get this kind of value. Okay, we will find the next one. So this one. Okay, so I'm multiplying by this row. Okay, so I will get 1 by A, 0 by B, 0 into B, 0, plus 4 into C, 4C, 3 into D, 3D, 2 into E, 2E. In the same manner, I'm going to find this one. So I will get 2A, B, 0, plus 4D, plus 3E. Okay, and I have to find this one also. 3A, 2B, 1C, 0 plus 4e. Okay, and I have to find this one also. 4a plus 3b plus 2c plus 1d plus 0. Okay, so I have found this value. Okay, so this value and this values are identical. Okay, so this value will be equal to 1, this value will be equal to 0, this value will be equal to 0, this value will be equal to 0, and this value will be equal to 0. So you have 1, 2, 3, 4, 5 equation, and you have 5 unknowns value. Okay. So you have to solve this 5 equation, and you can find A, B, C, D, E, F. Okay,